So I've already talked about how to solve some of these from distance time graph, speed time graph, so now this section is really just going through and actually calculating these things. So here, we talked about sort of speed is equal to the gradient of the distance time graph. So we've talked about that once already. So here I have an example of a table. Distance traveled 0 to 20, 100, 110 kilometers. Time taken, rate 0, half an hour, waiting an hour, 1.8, 2.3 hours. So from that, I can get my distance time graph. So we start at 0, 0, after 0.5 of an hour, right, we went 10 kilometers. After 0.8, we went 20 kilometers. After, this here, 1.8, we went 100 kilometers, and then 2.3, we went 110 kilometers. So I just plot those points, flip the dots. Right? That gives me just a rough idea at least of my distance time graph. Now from that, I can calculate speed by calculating the slope or the gradient. So here I have a different graph. So first we identify a straight section of the graph. So when you're solving for the slope here, you can't have a curved graph. For curved graphs, we would do something different. But for what we're doing a straight line. So we just pick out a part with the straight line. So from there to here. So we draw the horizontal and vertical lines, making the vibrating drills, right? Making a triangle, like we've done many times before, right? Then we calculate the lengths of the sides of the triangle. So from here to here is 1 hour, from here to here is 80 kilometers. So then of course the gradient is rise over run, or change in y over change in x. So that would be 80 over 1. So 80 kilometers per hour. Also, you just look at the gradients. Yeah, that's it. Nothing we haven't done already. We've done this in math. We've done this in algebra. So this is defined. This finds speed. So when you have a distance time graph, the gradient is equal to speed. This is the I don't know. So 3.10 to the something. I just don't remember what the something is. So speed and velocity, vectors and scalars. So this is just very short. We're going to get into vectors and scalars and that sort of later on in the next chapter. But I just want to basically give you an idea. So speed and velocity, they're similar, but they mean two different things, right? So both deals with how fast something is going, but velocity also gives the direction. So for example, I could say, the speed of the car is 110 kilometers, but the velocity of the car is 110 kilometers due north. So velocity gives a direction. And so the car is driving north. That's the only difference. So velocity is an example of a vector quantity. So whenever you see the word vector, it tells you need to add a direction. North, south, you can even say 60 degrees from north, 60 degrees south, something like that, right? So you have to add a direction for vector quantities. Another vector quantity is also weight. So when you go home, you weigh yourself on the scale, that's actually a vector quantity. It's the force that your body is putting downwards towards Earth. Downwards towards the center of Earth. Gravity. Right? So weight is actually a vector quantity. Speed is an example of a scalar quantity. So scalar quantities, same thing, right? They have magnitude, they have, something of speed, something like that, but they don't have direction. So vector quantities have direction, scalar quantities do not. Make sense? Yes, vector means a direction, scalar quantities do not. So temperature is an example of a scalar quantity. It's 10 degrees in. And its speed is an example. Time. I know, you can have that one, please. Okay, so anything, basically, some measurement of some kind without a direction. 20 meters, right? A length, something like that is scalar. But if I said, we're traveling 20 meters north, suddenly we have a vector. Speed, which is scalar, would just be 20 kilometers per hour. But again, we'll talk more about them in chapter 3. I just want to introduce them because it may ask when you use the word speed and velocity, you need to know the difference. So calculating acceleration. To calculate acceleration, we need two things: change in velocity and time. Because remember, acceleration is something speeding up, not increasing, right? So, from that we get this formula. So, acceleration is equal to change in velocity over the time taken. So, for example, if I go from 10 kilometers per hour to 50 kilometers per hour in, I don't know, 1 minute, which is a really long time, but it works, right? So, it would be a change of 40 kilometers per hour in, let's say, 60 seconds. So 40 over 60, that would be my acceleration, which would be kilometers per hour per second, which is weird, but that's how you use the units. So acceleration, change in velocity over time taken. So we can actually do that, write that in a different way. So, I realize that. So, acceleration is change in velocity over time taken. So then, these are the letters we usually use, A, T, V. A is acceleration, T is time, V is your final velocity, so in example I said it's a 50 kilometers per hour. U is your initial velocity, so the speed that you started. So like I said, would have been 10 kilometers per hour. So it's 50 minus 10, divided by 60 seconds, if it was my example. So you have to remember this. V is final velocity, U is initial velocity. So initial is where you're starting, final is what you end. Is everyone with me so far? No. Carlos, you with me? Seven? Okay. Okay. Oh, that's right. It's gonna be tough. Tough going for you. Okay. Can you at least cry outside so I have to go? That's the best part of the safe when you listen to this and you're like, what is that guy saying to his students? So, now let's do an example. Calculate the acceleration. So an aircraft accelerates from 100 meters per second to 300 meters per second in 100 seconds. What is its acceleration? The units for acceleration would be like length divided by time divided by time. So with your units for acceleration, let's take the example I could write. So this was the example I did, 40 over 60, 40 kilometers per hour in 60 seconds. So the unit would be kilometers for this example, we use meters per second. So that it's meters per second, which can also be meters per second squared, because there's 2 seconds. This is what you will see most often, meters per second squared, but it can be a difference. Fix your guess. What the square is so those are your units. So what is our answer to this one? 2 meters per second. Is it so first you do? Oh, right, it's a meter per second. What's square? How would you get to your final velocity minus initial velocity divided by time. Again, the time part. Final velocity minus initial velocity. If you start at 100 and goes to 300. So 300 is right and you want 100 starting. So 300 minus 100 you want whatever it is. That's the truth. 2 meters per second squared. So what am I thinking of? So this is exactly the same thing as we just did with speed, only now it's with acceleration. So for speed, it was the gradient of a distance time graph. Acceleration is the gradient of a speed curve multiplied by time. And how do you do it? You multiply by time minus acceleration is the gradient of a speed time graph. And speed is the gradient of a distance time graph. Distance time is different than speed time. We talked about both of these in the previous section. Acceleration so this one I'll just go through. Okay? So here I have my table. So from that table I can draw my graph. So this is time here in seconds, speed in meters per second here. And this is my speed time graph. You will, yes. And so I'm just like plotting the normal graph. Yep. Time is that. Exactly. And then once I have this straight line, I calculate the gradient, same as what I did before. So in this case, the gradient is 0.2, so that gives me 0.2 meters per second squared as my acceleration. You just rise over run. Rise over run, exactly. In this case, each square, the bigger square is 5. So, any questions? Yes. Your question is, that's the question. My question is the question.